Hi, Roberto. How are you? I was hoping you could introduce yourself and provide an overview of the project we'll be talking about today.
Hi. I'm Roberto. I'm currently a postdoctoral fellow in the lab of Mary Watson at the University of Delaware. But the project we'll be talking about today is actually a project I did while I was a PhD student in the lab of Doug France at the University of Texas at San Antonio. And really, this was kind of an offshoot project that stemmed from a collaboration that we did with the process chemists at Bristol Myers Squibb. And so we were kind of looking at some new palladium reactivity. And one of the things that we ended up doing was actually trying to detect some of these organometallic intermediates using high resolution mass spectrometry. And this kind of led to a whole rabbit hole that I went through in my like the last 2 years of my PhD.
That's great. Yeah, so how specifically did you become involved with this work? How did the project come to be in terms of how it was originally presented and then your involvement?
So the project really originally started from what was actually an ongoing project at BMS. So they had reached out to basically have this collaboration with us that really, for the most part, focused on developing the methodology and being able to optimize the methodology for very specific substrates that they were working with. So part of our job then became just trying to generalize a lot of the methodology that they were seeing. And I separately really became curious about the actual mechanistic understanding of the reaction itself. So that is really where, aside from just the traditional things that you see from a lot of organic labs, of just develop the methodology, make a substrate table, we actually decided to delve a little bit further in starting to look at the mechanism of this reaction.
Very good. I'd be curious to hear more about what inspired the interest in using high-res mass spectrometry for this approach.
So, really, that kind of came towards the beginning of us looking into the actual mechanism for the reaction. The way that it began is we actually kind of started very much with some of the traditional tools that we think about when looking, especially when we're using phosphine ligands for our catalyst. So we were looking at everything from phosphorus NMR, looking at a lot of proton NMR, trying to and really looking at stoichiometric reactions to kind of see if we could see some of the species that we actually had in solution. Now, unfortunately, we were getting very strange results that we couldn't completely explain, at least not from a lot of what is normally thought of with a lot of palladium catalysis. So we kind of just threw it out there to the wind and decided, hey, we have access to these very new mass spectrometers. So why not see if we could use that to help us actually figure out the structure? Because that's one of the things that, since you don't really, most of us in organic synthesis or even in organometallics, yeah, we have to characterize everything by high resolution mass spectrometry, but we rarely think about the fact that you can use the fact that it is a high resolution instrument to actually then start to make informed decisions about the structures of these things that you're seeing in solution. So, using that kind of knowledge base, we started to play around with the mass spectrometer, which then ultimately informed me towards the actual organometallic synthesis of trying to actually identify these complex palladium complexes that we were seeing in solution.
You may have just touched on it, but I'd be curious if you could expand on some of the primary challenges you faced in the process.
Well, the biggest thing really was the fact that we were dealing with a reaction that was air sensitive, right? For most of the things that we do with LCMS in particular, you're normally preparing your sample in air and doing all these manipulations in air. But then now that we're dealing with organometallic complexes that in many respects can be air sensitive, we actually that really kind of became the biggest challenge, is how were we going to start to prepare samples and manipulate them in such a way that we would minimize any changes to what was happening in solution in the actual reaction.
That makes sense. I was hoping you could touch on the sample preparation steps required and talk about why some of those steps are critical to ensure the right results.
So in the beginning, we actually got rather lucky that the complex we were looking at was very air stable. So for those, it was simply taking an aliquot of our reaction and doing very similar things to what you would do for like standard HPLC analysis. Take the aliquot from the reaction, dilute it down, usually with something like acetonitrile, but normally a solvent that would be friendly with the mass spec. But once we started to venture into looking at other palladium-catalyzed reactions from like the canonical literature, that is where we actually started to look into other aspects of how we were going to have to prepare these samples. And what we realized the hard way was that keeping oxygen out of a lot of these systems was very necessary, just because a lot of phosphine ligands are very easily oxidized with just oxygen in the air. And that can lead to other structural changes in what you might see on the mass spec. So it really came in to figure out ways to introduce our samples air-free, being able to use any degas solvents and dried solvents. And specifically, what ended up happening afterwards was having to figure out a way to filter our solvents without introducing too much air into the system. Because as anyone who's really dealt with any amount of mass spec in general, I kind of know that having a lot of solids or stuff that can easily become insoluble is a problem, just because now you can start to damage a lot of the components in the mass spec. So being able to do these filtrations air-free and a lot of our manipulations air-free kind of became the next step of what we were trying to figure out.
And if I heard you correctly, I believe you said that you're focusing more on dilution rather than concentration for
Yeah.
sample prep. One interesting thing I've seen, just for background, my company makes evaporation equipment used for sample concentration. And because we're utilizing nitrogen, one thing I've seen where people need that inert atmosphere, rather than doing the reaction in a glove box and
Mm-hmm.
then transferring it to the evaporator, they do the reaction and the drying down under nitrogen,
Mm-hmm.
which is a great solution for preventing that oxidation. But obviously, when you need to dilute the sample rather than concentrate it,
Yeah.
it's not a good solution for what you're doing.
Well, especially with us, so we didn't have, our lab didn't have a glove box. So we weren't even doing the initial manipulations. Like the actual reaction setup was all done on the bench top, and then the vessels usually purged out with nitrogen. So that was kind of the bigger issue there, was the fact that we weren't even dealing inside of a glove box. The glove box would have probably made things a lot more straightforward because everything's already under an atmosphere. But the fact that we weren't kind of provided these extra challenges for us. But I think at the end of the day, though, I think it better helped informed us to basically try to make this method as friendly as possible, right? Because I mean, just like our lab didn't have immediate access to a glove box or easy access to a glove box, a lot of labs out there might be in a very similar situation to what we might be in. Or just the fact that it would be easier to manipulate everything on the bench top rather than having to go through a glove box for everything.
I think focusing on making your method as friendly as possible is a great approach, knowing that every research lab out there, they're going to have to do the work with the tools they have
Mm-hmm.
typically at hand and just dig in. So yeah, I can certainly appreciate the approach you took. I'd really like to hear about anything else you'd like to highlight in terms of the outcomes of the project, in terms of why this work is important, and anything else you'd like to share with the audience.
So, kind of the big takeaway that I actually ended up coming from this project was I mean, not only the fact that, yes, we are able to detect these complexes at very low concentrations, which was kind of the big thing for what we were trying to do, but actually the fact that, you know, when it comes to a lot of organometallic catalysis, one of the big things that we end up having to worry about is actually off cycle species. So these are usually species that just throughout the reaction time or because of the reactivity of certain complexes, they just form but don't ever really result into any productive chemistry. But we are actually able to very easily identify these. And one of the things that we were able to chronicle for a completely unrelated project where we were trying to develop this palladium chemistry was the fact that we could not get the chemistry to completely work. We always had these strange byproducts that we were forming that we had identified but weren't completely sure about where they were coming from. But then, just by a few experiments on the mass spec, we were actually able to very easily identify these off cycle complexes that, once we knew they were there, explained everything about the byproducts that we were seeing. So it really started to then start to inform us about the types of structural changes to ligands that we could make, any changes that we could make to our conditions that would basically yield a much cleaner reaction profile.
That's awesome. I really appreciate you sharing your work. I really appreciate the time today. Thanks for sitting down, Roberto.
Yeah, thank you.